We are continuing the wonderful tour de force of the Yuval Fest, and our next speaker is Volker Soergel from University of Heidelberg, and it's a great pleasure to call on Professor Soergel to present his lecture on the next large accelerator project in physics.
Okay, thank you. Well, it is a great pleasure and honor to be here for this wonderful occasion. I'm pleased to see Professor Neeman in such good spirits. Congratulate you for your birthday. And I would first start with two recollections. I remember two visits you paid us at DESY during my time at DESY. The first visit has been in 1983. And you have a picture of it. So it's documented. That's the wrong. Here you are. Pardon? You have been by 22 years younger, obviously. Yeah, it's okay. That's okay. We did not drink beer here. It is apple juice or something of that sort. You see Heisenberg and other people. At that time, Professor Neeman was in Germany in his capacity as a Minister of Science, and he had probably other things to discuss in Bonn than high energy physics, but he had a very important mission. He convinced our then Minister of Science, Heinz Riesenhuber, that HERA was a good project. And probably Riesenhuber was surprised to have a colleague as a science minister who was a top world expert in particle physics and told him he should approve the project. He did so later. So thank you very much for your support. And about that time or afterwards, it must have been afterwards, you made an effort to get Israeli groups, an Israeli group involved in the construction of HERA. HERA was, I believe, the first high energy physics accelerator which was built with a wide international participation. Israel was part of it. You helped to get this out. You had a second visit, which was in 1988, January, where you gave two wonderful lectures in our auditorium at DESY. This was the first lecture on Medved. I cannot just recall it word by word, but it impressed me very much. It's a pity you didn't succeed so far to get it through. The second lecture was on the inflationary universe. So I did not understand any word, I must admit, but it was an interesting lecture. So we are very pleased. So at the same time, I must say I'm happy to be here in Tel Aviv and in Israel again, meet so many colleagues and friends who have been working for a long, long time at DESY. I see Eisenberg here, the others who have been done very good work, both from Weizmann Institute and from Tel Aviv. And this was your initiative and your support that this kind of good collaboration could start and could be continued for such a long time. So thank you very much. I will talk today about something more down to earth for my spirits than general relativity. I will try to convey to you our present situation with a new accelerator project which has been planned and discussed for a long time and which has made a step forward, I guess, in the past year. The question of a TTV linear collider to be built as hopefully the next project in particle physics. First, a few words for the motivation. This kind of talk has to start from the standard model. The standard model tells us about everything we know about particle physics. it has its roots in your discovery of SU3 symmetry and in the understanding of weak interactions in the late 50s. Now, up to now, the standard model describes all experimental observations. It seems to be rock solid and not very easy to find something which goes beyond the standard model. But there must be something else. We all know that. And the something else, in our present understanding, must be at masses which are not attainable with our today's accelerators. That's the reason why we would like to have accelerators of higher energies. Now, for higher energy, we will have a big accelerator from 2 years from now at CERN, the LHC, the Large Hadron Collider, which is colliding protons on protons, 7 TeV each, and then hopefully produce particles of great mass. However, we can probably find those particles at high energies. This table of accelerators. The LHC will be here. And with proper detectors also identify new things like Higgs boson or supersymmetric particles or something like that. However, proton-proton collision is something very complicated. And it's difficult, it's impossible to know what were really the initial state. We can measure the final state. Now, if we know the final state, we can measure its mass, but we cannot measure much of its properties. And we may end up in a situation that we believe we have found something, but we don't know what we have found. And this is the reason why we believe that one should have a different facility which can also understand what we have learned. And this different facility is this TeV collider. There are, of the standard model, a lot of open questions. I will not go through all of them. An important thing is that within the standard model, we still have not found the Higgs boson, which is supposed to get us closer to the very fundamental question, how does nature impose mass on matter? I hope to find the quantum of the Higgs field, and so far is one of these particles we didn't find, which is still within the standard model. And I will exemplify the problem I just talked about, that we will not easily learn from the mass what is really happening. We know something about the Higgs boson from the radiative corrections to the Z0 production by E plus E minus collisions. This was in Janos' talk yesterday, he talked us about it. And we should find the Higgs boson somewhere in this chi-square curve. Up to here, we have not found it, so maybe it is at somewhat higher mass. Now, if we have found it, then if we have found something at that mass, which has a one proper decay channel of the Higgs boson, we still don't know whether the Higgs boson is really there. In order to really prove that we have the Higgs boson, we should measure, for instance, its decay properties in various final states, which are listed here: 2 photons, 2 Ws, 2 electrons, 2 charm quarks, B quarks, and so on, depending on the mass of the particle. Only if those decay rates are the ones we expect in the standard model, then we can say we have found the standard model Higgs, otherwise not. And this is one of the processes where it is true that the LHC alone will probably not give us the answer, and another machine may be necessary. The thing is even more difficult for supersymmetric particles, which have very complicated decay properties, with many neutral particles in the final state. And even there, although there it may be difficult to find this. The expectation is that with a Electron Collider, we can do much better because we know the initial state precisely. Electron Collider would collide, well, there's a better picture, I believe, of the Electron Collider. Maybe not. I lost it. Electron Collider, here it is. Electron Collider would start with an initial state, electron and anti-electron colliding. So we know very well, we can know very well its energy. We can even know its spin. So we have really the quantum numbers and we can do a very good analysis. This is a picture of an event at lab, which decays in 2 jets, 2 quarks and 2 muons. It's very clean and we know almost everything. The production process with simple kinematics, we know the quantum numbers, we know the cross sections, we know the polarization, the energy momentum of all partons we can measure, and the energy system can be varied at will of the accelerator. This simplicity convinces us that even going to much higher energies, Electron Collider would be an extremely good instrument. And that's why there is a common consensus on the particle physicists since many years that besides a hadron collider, one should have electron collider, then going forward to the new energy frontier, which will be available at CERN with a lab machine. This electron collider should have an energy in the TeV region for the center of mass, means 500 GeV and 500 GeV probably, and it should also have a high luminosity in order to get a reasonable rate. Why such a high luminosity? Well, the problem is that when you go up with energy, the cross-section goes down like the square of the energy. And so if you want to get some rate at high energies, you need to go up with the luminosity in order to achieve something. This is a big challenge for such a lambda collider. I have on this graph are the challenges for the Electron Collider. Where is it? There. Okay. So this Electron Collider could not be a storage ring. Why not? The electrons, when circulating in a storage ring, they irradiate the energy. And the energy radiation, the energy lost in a turn goes up like the electron energy to the 4th power. I wrote here the formula that the energy loss is the 4th power of the energy divided by the 4th power of the mass times the radius of curvature. And I give a number of examples. 3,000 meters is a big lab ring, the radius of curvature. When this ring is run at 70 GeV beam energy, the energy loss per turn is 700 MeV. Now, if you go a factor of 3 up in energy, you see that it's not possible. You have a few GeV accelerator in your tunnel. It doesn't work. You run against a brick wall. So this is the reason why we cannot use a storage ring as we did before so successfully with the storage rings lab, Petra, and so on. If you could use muons, some people dream of muon storage rings. The situation would be totally different. However, this is not practical at the moment. Maybe some people invent some clever scheme. So far, we are limited to electrons. So the big challenges, so the only technique we can think of at the moment is to have a linear collider, a machine where 2 linear accelerators accelerate a beam, which is then brought into collision at the interaction point at the high energy. To build such a device has enormous technical challenges. First of all, as I told you, we need to have a high luminosity. The current we can accelerate is limited by beam dynamics. And so to get high luminosity, the only chance is to have small beams. And the beam sizes which are in question are vertical 5 nanometers as interactions, 5 nanometers. So the two accelerators should be precisely enough adjusted so that you get two 5 nanometer high beams fully in collision. And the width is 500 nanometers. It's one challenge. The second challenge is to get linear accelerators with high enough gradients so that you don't go over hundreds of kilometers, but really have a reasonable size. Reasonable size is something like the circumference of the lap ring, or a little bit more, 30 kilometers or something. And this is quite a technical challenge. The single collider, the linear collider, has had a model. So it has been proven it works. And this is the famous SLAC linear collider, which is an ingenious idea to use the famous SLAC linear accelerator to have in one cycle an electron bunch and a positron bunch running down, having a magnet here separating them and colliding them here. This system indeed worked. You can see here that the people have produced reasonable luminosity by getting this function of time. In the end, it reached almost the theoretical expectation, or half of it, by shrinking down the beam to small sizes over the years. So we know that such a linear collider can work. And we also know that the focusing is possible. There was, again, at SLAC, an interesting experiment, the final focus test beam, which used the beam of the linear accelerator with a special lens system. It was a 5 or 6 country collaboration. And they demonstrated in that experiment that the beam can be shrunk down at that time to 40 nanometers, but this was what expected for this kind of optics available, and this convinced us that one can do the proper shrinking down of the beam. With these two inputs and with the high energy physics motivation, several groups started to develop the technology for this kind of linear collider. And I will now come to this point. I present you with 3 projects which have been developed. The first one is the so-called NLC, Next Linear Collider, developed jointly by KEK, who call it JLC, and SLAC. Here is a machine. You have an electron linac, you have a damping ring to cool the beam down, and then you have this long, 15-kilometer long linear accelerator, which accelerates the beam up to some 250 GeV or 500 GeV, depending. Here's the other one, and at this point, there's a collision point. This energy, this machine uses for the linear accelerator a very high frequency, 11 gigahertz, and uses copper structures, as they have very good experience with these kind of things.
Why is there such a funny angle here? It's not affected by.
This has a good reason. I come to that later. The second device which was developed was the so-called Tesla machine. This was developed by a large collaboration of scientists from many countries. I show you here the flags. This machine uses, it goes back to back. I come to this later. Otherwise, it's the same principle. You have 2 linear accelerators. Now here, niobium cavities are used, and they're operated at 2 Kelvin superconducting. I will come to this point too. I mentioned here that the driving force behind this Tesla project was Björn Wieck, who died tragically 5 years ago. The third project, which was developed, is at CERN. the click machine. The click machine is an innovative device which, contrary to the previous things, the previous are more classical linear accelerators which have cavities and which have glystrons. The click machine does not have this. It's a two-beam machine which accelerates, which has one driving beam, which then produces the radio frequency, and in this way can achieve higher gradients than the other machines. The click machine is supposed to get a gradient of 170 MeV per meter, which is enormous. The Tesla machine is supposed to have a gradient of 35 MeV, and the NLC machine is expected to have a gradient of 50 MeV, somewhat higher than you can achieve with a superconducting machine. These three devices have been developed now over several years in SLAC and in the Tesla collaboration about 10 years or so. And both these systems have reached a state of maturity that one could decide whether or not one wants to go ahead. Meanwhile, the physics community has realized that there may be perhaps a chance to build one of these machines in the world, but probably not two, because these things are too costly. And this is when ICFA came on the play. ICFA is the International Committee for Future Accelerators. And this committee is looking at these big projects and trying to get the people to join into the projects and to make the proper international planning. Now, this ICFA committee came to the conclusion that really one collider worldwide should be built in international collaboration. They defined the parameters, I will come to that. They wanted to have a technology decision in the year 2004, means a decision which of these three projects should be followed up in order to make really a joint machine. In order to get this decision, they called for an international technology recommendation panel. These were 12 people, 3 of Europe, 3 from North America, and 4 from Europe, 4 from North America, 4 from Asia. These 12 people were also called the 12 wise men. And these wise men were supposed to recommend technology which should allow these two things. Should allow a decision and the start of construction before the year 2010 and a start of operation in 2015. This means these wise men were asked to find out whether the technology was viable, but whether it was also mature enough to go ahead in this time span. The parameters given are here. It should be a baseline machine which can operate from 200 to 500 GeV. It should provide in 1 year 125 inverse femtobarm. This corresponds about to the 2 times 10 to the 34 I mentioned before. The electrons should be polarized if one wants to do it. Secondly, the machine should be upgradable to about 1 TeV in the center of mass, and one should have an even higher integrated university in 3 years for the reasons I mentioned before. And thirdly, one should have as an option the positron polarization of 50% and perhaps the opportunity to run at much lower energies if one wants to come back to the program of lab with Z0 production. 12 people met over the last year many times, and finally came to the following conclusion. The first conclusion was, and this was already told to them early, that probably the click, apart from its, in spite of its very innovative design and technology, could not, certainly not meet this time scale. If it would be 10 years later, perhaps, but not at this short time scale. So the real decision had to be taken between the 11 gigahertz warm copper cavity device or the 1.8 gigahertz cold device. The conclusion of the panel was that the superconducting technology should be chosen, and that now all the laboratories active in this field should unite behind this technology and make a new proposal based on the existing R&D carried out by the Tetra collaboration for the accelerating structures, but for the R&D of the other laboratories, KEK, SLAC, and so on, for the other systems, to make a joint new design. So the recommendation concerns the technology and not the design of the machine. It's not just a copy of the old machine. In particular, as the Tesla machine, you have seen, was planned to go up to 800 GeV. I think it was on my slide. And this machine should really go up to 1 TeV safely. Now, I go quickly through the reasons which led to this kind of recommendation. The first thing is that you're surprised it will not, the reason will not be only the gradient of the cavity. You remember the cavity of the War machine was 50 MeV per meter, and the Tesla machine was smaller, 30 to 35. So here are the reasons why this was chosen. First reason is a large aperture of the cavities. The cavities in the Tesla machine, in the cold machine, have an opening of 7 centimeters. 7 centimeters, right? The cavities of the 11 gigahertz machine have an opening of 1 centimeter, 10 millimeters. Now, what is bad about this? When you send the beam, a bunch of particles, bunches, a train of particles, bunches through this machine, then the first bunch will excite some wake fields. And the following bunches, this will increase, and the following bunches in the bunch train will feel those wake fields. Now, if your beam is not exactly centered, these wake fields are asymmetric, and they will distort the late-coming bunches. And if you have a distortion of the beam in this accelerator, then you can forget about your luminosity. This effect is sensitive to any displacement, and the sensitivity goes like 1 to the r square or r to the third power something. So when you have a 7 centimeter opening, you are 2 orders of magnitude less sensitive to this kind of wake field effect. And this has, for instance, consequence for the 10 gigahertz machine, I think it's about 10 microns. One has to be sure about the long machine, and in the other machine, correspondingly, less half a millimeter or so. This has consequences for the adjustment of the machine, which is possible technically doing, but very difficult, and also has consequences for the selection of the site, obviously. One reason. The second reason, and now I come to Fritz's question. You have to wake up now. You have, is the long separation of the bunches. In the low frequency machine, the bunch train is 1 millisecond long, 300 kilometers. And separation of the bunches is 300 nanoseconds. This is very helpful for 3 reasons mainly. So one reason is that you can, at the interaction region, when the bunches don't meet exactly in the 5 nanometer, you can have a feedback from bunch to bunch. Gets the thing stable. The second reason, the second good thing is that the physicist in this detector has a distance of 300 nanoseconds. And then with a time delay detector, like a time projection chamber or something, you can separate the particles from bunch to bunch. And this makes detector building probably somewhat easier, a lot easier. And the third thing is now the thing of Harald Frisch. Now I have to come to the other machine first. The 11 gigahertz machine has a bunch distance of 1.4 nanoseconds. So these two things are not possible. Now the third thing is that when you cross these two beams, you have to make sure that inside the interaction region you do not have 2 or 3 bunches colliding. And you have to make a crossing angle so that only one bunch collides, and then out of the collision they are well separated. And this imposes the crossing angle of 20 milliradian. Has this been your question? Okay. So for these three reasons, it is better to have a low frequency in a long bunch train. In the end, I believe in order to separate the beams after the interaction, I believe in the cold solution, when we'll make a 2 milliradian or something crossing. But it's nearly head-on, which for some physics applications may be nice. Now, a second reason is that the main Linux system in the superconducting part is comparatively lower risk, contrary to what people may expect. And this is mainly due to the large technical development, which is now fully industrialized, and there's more experience than with other systems. A third very important reason was the fact that at DESY, Germany and some European countries will build a 12 GeV machine with exactly the same technology, using the same cavities, with the same RF structures and all the same logistics, starting in 2006, in order to have a free electron laser for X-rays. And so this is a full, small size, 5% prototype of the big accelerator, which is nice, and you can learn a lot from this. And last but not least, the use of superconducting cavities reduces the power consumption. And this is not a small amount of power. These beasts eat power a lot. And so the power consumption, I think, is at the full energy about 100 megawatt saving or something like that. Huh? It's quite a lot. So these are the reasons why this thing was chosen. Remember that for these reasons, one buys a machine which has a lower gradient. So the machine has to be longer to get the same energy. However, this committee considered this as a worthwhile loss. I will now come to a few technical details of the. There's something on this graph. Why is that? Surprised. I said, oh, okay. Some technical details which show you how this development for the cavities went, which was one important thing, and some other special technical aspect of the cold machine. The cold machine up to now and also in future will be built probably of this type of cavity. It's a 9-cell cavity made of pure niobium. The thing is made in a simple fabrication mode. These parts are pressed and then they are electrowelded together. Remember that of these things one needs about 20 to 30,000 this whole machine. So it's a big, big job to do it, but the industrial production seems to be reasonably well underway. Here is the gradient which could be achieved in these cavities. That's time. We are now in the year 2005, 2000, and you see we have now here something like 40 megavolts per meter. When the development started for Tesla, it started about here, 12 megawatts per meter, which was achieved at Cornell. And this, at the time, this gave the trigger to start the Tesla development. And then, over the last years, this development was very successful. Now, naively, you can now extrapolate this kind of curve. It's just normally done, these kind of things. But unfortunately, there's a physical limit, which is about here, due to superconductivity. If you go to higher fields, then the current in the cavity makes a strong enough magnetic field to drive the superconductivity out. And I find this plot extremely impressive, because when we started here, this development, the Tesla collaboration started here, all what had to be done was to improve the surface. There's all surface problems and cleanliness of the niobium zone. Now these things seem to be so well under control that one has approached nearly the theoretical limit for this kind of cell. There has been now a proposal of a Japanese group to do it differently, to do a different shape. This could perhaps, this is the present shape of the Tesla shape, and this shape should bring at this outer skirt, here is a big magnetic field, should have a lower field here. In this case, maybe one can gain 2, 3, 5 megavolts more. Whether other things are as good, we don't know. It has to be tested. I show you here one graph of the performance of such a cavity. Here is the acceleration gradient, 35, 40 megavolt, and here is the Q value of the cavity. And when the operation should be at 35 megavolt, this should be the conditional point. So we have enough headway in this kind of cavity to operate at 35 megavolts. This is one cavity. There are several of this type. And one has to see whether one has still to develop the scheme in such a way that the series production gets this very good performance. However, if one gets this kind of good performance in 5 or 10, I'm quite optimistic one can achieve that thing. This advance in gradient was rather recent, and it was achieved by adding a new treatment, so-called electropolishing. Up to then, the people did some chemical treatment and heating up and rinsing and so on. And then the electropolishing came, which was done at KEK, which was not part of Tesla at the time. And so it seems that this is a real big step, which can help to make the cavities to that good performance. So the cavities, we believe we have a model. We know what to do. If it can be better in the coming years, it's nice. But otherwise, technically, it seems to be solved. Let me add one more point where the cold machine is different from the warm machine. The cold machine needs, in this 1 millisecond of punch, many more electrons, 20 times more positrons than the cold machine. And so you have to do something special for the positron source. This is not easy. And the scheme which has been chosen in the proposal is to use the electron beam, sit through the now I'm here in the mess to find Tesla back. Tesla is gone. Too bad. So here is the scheme. You send the electron beam through a 100-meter wiggler, 100-meter undulator. And this undulator produces 20 MeV gamma rays. The gamma rays are converted in a target, then accelerated to 6 GeV or something, and then they produce, and convert to positrons. 6 GeV positons are accelerated and then sent to a damping ring. This is a demanding technique. One has to have first this beam of the electron accelerator. It's a primary beam which goes through, which then later on comes to the collision. So the beam is used twice, first to make positrons and then to collide. This technique has, compared to the standard technique where you have just a 6 GeV accelerator and put it on a tungsten target or something, it has an enormous advantage that you don't produce so many neutrons. And also you use less energy, I think. It has another advantage. If you once have developed this scheme and you want to make the polarized positrons, you have to replace this Wiggler by a helical Wiggler, and then you get automatically polarized gamma rays, and you get automatically your polarized positrons. Now, one reason in the discussion was the industrialization, which was already far advanced. I show you here the treatment of the cavities. That's what I was looking for before. You see that this work has to be done under clean room conditions. As soon as there's a little spot in there, then the cavity is gone. You have no high gradient. It's very careful work. Another important thing is, of course, that you need to have glystrons. And here, the low frequency has an easier life, as the 1.3 gigahertz is a common frequency in electrotechnics. And we have now 3 manufacturers which can sell these high power glystrons needed there with a long lifetime of $100,000 right from the shelf, more or less. There's a 4th company developing that thing, and this seems to be very well. In the end, one will build out of these cavities so-called cryo modules, which are 8 of the cavities, 10 of the cavities in one pipe, and then you put these pipes together in these modules, and the whole accelerator will be then built up of these kind of pipes. DESY has a test accelerator which can operate at 1 GeV. It's normally not operated at that energy because it's used for VUV operations and has some schedule there. Now, I stop here with my technical stuff, but would like to tell you a little bit where we go from here. I start with the recommendation of the wise man. I'm happy to tell you that this recommendation has been received very well, not to say enthusiastically, by all the laboratories, also those which had before developed the swarm thing, which was very gratifying for the committee. And now a global collaboration has started almost immediately. We had our last meeting of this wise men in August. I think in November it was a full-fledged meeting in KEK. The second meeting now was at SLAC this spring in March. And the third meeting will be in August. So the global collaboration has started. And we have even a chairman for that. It's Barry Barish from Caltech, who is the chairman or the director of the global design effort. This global design effort has 3 regional centers in Asia, Europe, and the United States. It is expected to provide, by the end of this year, a basic design of the machine, which is in its performance defined by the parameters I showed earlier. So it should go to 500 GeV first and then to 1 TeV with all the qualities I have mentioned. The conceptual design report is expected then by the end of next year, including the costing for 3 sites. This looks incredibly fast. However, remember, 3 laboratories have done for years development work, so the pieces which have been put together are more or less known. And for the accelerator part, we have a model which can be used. Maybe there is some improvement, but for all these parts, there's a lot of experience. For the beam transport and things like that, beam position monitoring and so on, there's an enormous experience in SLAC, of course, from the time. And in KEK for other things, so this seems to be possible. There are now 5 working groups built in this global design initiative or effort, which are discussing special items to be decided upon. I did not talk about cost. I did not talk about site. Site is very difficult because the site has to be decided probably politically, as long as there are no geological problems, and the country which will be the host for that facility will have to take a big share of the costs. Cost, there is no cost evaluation for the new machine, of course not. There was a cost evaluation for the Tesla machine, where DEC and the Tesla collaboration had provided a design report. These costs are published, and I can tell them to you. What they mean, I don't know, but it may be interesting to see what it is. For the Tesla machine, for the baseline, the installation cost back 3 years was 3.2 billion euro plus 7,000 man years, so it would be about 3.5 billion euro. If the machine goes to 800 GeV, it does not go up proportionally, because at that time the full length of the machine was equipped with cavities and with cryogenics, and was planned was to add more glystrons in order to increase the gradient of the cavities. In this case, the increase of cost would have been some 500 million or something. So that's the number I have. For the new machine, it will be probably more, but the wise men were asked to report also whether cost differential would be a reason for the decision. The answer was no, because it was at that time not precise enough. And what was a great achievement of the Tesla collaboration is that the superconducting price came down to the same level as the warm price, which was at the beginning of the operation not clear at all. This was the aim, but it was not clear at all. So this was a great achievement for that. So for the site, of course, I cannot say anything. There is for this global design, the global design effort works towards a new design on the basis of the existing R&D results. This, I think, must be stressed several times. The organization of this global design effort is apparently done similar to the organization of a big experiment. So that you sign memoranda of understanding. And I learned 2 days ago that this MOU for the global effort has already been signed now by 10 states, which is very nice, including Russia and the others. An interesting point is that the governments take an interest in that thing. That's very healthy, so that they can follow this cost development and hopefully make spare money to build the machine. It's called FALC, Funding Agencies for the Linear Collider. They have regular meetings, and they did it even before the wise men came out with their statements. And the members of that business are written here. It's Germany, it's UK, France, Italy, US, Spain, Canada, Korea, Japan, and Keck, India, and CERN at the moment. There is some other activity from Europe. This is some funding for design of beam control elements. It's called EuroTEF, and several countries and laboratories take part, including CERN. And this money is especially spent inside universities in several countries. 27 institutions help with their staff to do some development. I lost my last slide. There's of course also some detector development going on, but I will not talk about that. There's detector development in this country, and some interest in this country, as I know. But I can come to a summary. First of all, let me say I think this linear collider is a really worthwhile project if you want to make good progress in particle physics. The timing which was given that one should hopefully have operation in 2015 is probably the fastest one can do. I think it is very important to go fast, so that there is a good overlap between the LHC, the proton machine, and the electron machine to have a cross-fertilization of the results. This has been proven to be extremely useful in the past when we had these lepton colliders and hadron colliders. It is an enormous project. If I didn't underline this and made it too easy, believe me, it's an enormous project. It will probably be 40 kilometers long. It has a high technology in these cavities. It has a high technology in the positioning and many, many things. So it's a very demanding project, and will have interesting work for many people. It's a real challenge. I hope that many countries will join this thing. I hope Israel will join it. I understand that some of my colleagues are already working on some things which are also related to the machine. Detector technologies are being developed. The superconducting technology, I believe, is good developed. This target for commissioning, well, okay, let's see. I'm not so sure. But one thing is for sure, that this process of the ITRP, the International Technology Review Panel, has given an enormous impetus to this whole thing. And it is very nice that, very promising, encouraging, that the world community in particle physics is capable to do such a process in such a way which gives us a good feeling that hopefully the push inside the community will go on, perhaps for realization of the project. Thank you.
Thank you very much, Professor Soergel. Quoting you, you exposed us to future horizons for understanding the universe's origin. Comment. Yuval.
Yes, I have. First, enjoy very much also both the memory of the past and the new project. I should say that maybe you don't know it, and it's not well known, but I was involved in helping out with another accelerator on the German side. That was when CERN was going to build the first collider. Germany was, I think, paying for 30-40% of the collider, and Heisenberg came out with a statement, negative statement. I had 2 occasions in which I was involved with and had for a few days information with Heisenberg, and there's also a story in which Harold we see the other side of it. But in 1969, I stayed at Buell Paris for a few weeks, and Heisenberg came to Paris to get an honorary degree at the École Polytechnique. And then he stayed in Europe for 2 days. And he had just made that negative statement. So I asked him, why do you think it's not a good idea to build this collider? He said, well, because I have a theory, and give me 1/10 of the money to have people help me with some calculations. And I tell you what happens at any energy. So it was a problem. And I thought, how can one overcome this kind of situation? And I thought about it in the evening, and the next day for breakfast, we had breakfast together, and said, well, Heisenberg, thought about what you told me, but there was before you one very important scientist also. His name was Aristotle, and he thought he had a full picture, and then he considered to be the cause of the stopping of science for about 5,000 years. Would you take that risk? You might be also. So he said, well, you got me, I have to think it over. I thought it was not a bad, to be compared with Aristotle, was not something that could be construed as a disparaging comment. And a few days later he told me, I thought about it and I'm withdrawing my statement. And I think it helped in going ahead with this thing. So in that collider also there was this problem. But now, having mentioned Heisenberg, I have one comment which is, I mentioned there was I wrote something about Feynman, and there was this in the, I wrote it for Haaretz, and it was I think it was in the Herald Tribune, and among other things, I explained how Feynman was intervening in colloquia and in lectures and seminars, and was making sometimes life miserable for that person. And I was not pleasant when that happened with Heisenberg. I think Harold must have been there, and I think he was very sharp with Heisenberg talking about his theory, and I quoted some word that Feynman used, like your theory is crack or whatever, and I got a letter from somebody else who said it was not crack, it was schmack or something like that, some other word. So that's the only correction I got on that thing. But apparently he had made it very hard for Heisenberg on that seminar. And that's the witness was Harold and not me in that case. I only can say that I saw also, for once, the other side of the coin, when Geber, the Norwegian physicist, Nobel Prize, and when Geber gave a colloquium at Caltech, and Feynman jumped also on him, but he had prepared a trap, and it made Feynman look terribly silly. After that, things were different. So there were answers to that kind of situation.
But I think it is true that we had with Heisenberg problems at several projects, not only at ISR. It's true, yeah.
It's almost,
but in the end, he was helpful to operating CERN. So.
Professor Soergel, you were one of this vice person in the committee. So, if I were to ask you as a vice person, on which country would you bet the ISC when you build?
Yeah, we didn't go into that. But at the moment, Even you can read in the newspaper that the DOE people state that they would like to get the machine into their country. Now, if they manage to get the funding for being the host, this will probably be the solution. Now, to go a little bit further, there was a proposal to build a Tesla machine in northern Germany, as you know, and that would have been also interesting from another point of view, where you were yourself involved in, to use a linear accelerator and collide it with a beam in the Hera machine, right? Whether such a site can be found in a different place, I don't know. It seems to me that even at the Fermi Labs, this may be difficult because the region is so densely populated. Otherwise, this is a likely outcome.
Any other questions? Let me just say that the last exchange really reflects on the asymptotic freedom in the action of theoreticians, but the constraints of the experimental world are much more profound. We would like to express deep thanks and appreciation to you for a magnificent